Hello and welcome to all students. In this lecture, we learn about a linear transformation. Outline of our lecture is, first of all, we see the definition of linear transformation, and then we see examples on linear transformation. The definition of linear transformation is, let capital V and W be vector spaces over the same field K. A function L from V to W is said to be a linear transformation if for any two vectors u, v in V and any scalar C belongs to K, the following two conditions are satisfied. First condition is L of u plus v is equal to L of u plus L of v, called as additivity or operation of addition. And second condition is L of cu is equal to c times Lu, L of u. So homogeneity of degree 1, or it is called as operation of scalar multiplication. If our function L satisfies these two conditions, then we say that function L is a linear transformation. Here, function L is called as a linear map or linear transformation. We write note. Thus, a linear map is said to be operation preserving because operations are preserved. On the left hand side, there is addition of two vectors, and on that vector we are operating L. And on the right hand side, we again get the vectors, addition of vectors, but these vectors are from the codomain. Addition of vectors from the codomain. Similarly, in the second condition, L is operating on scalar multiplication of vector in domain, and on the right hand side it is also a scalar multiplication, but that scalar multiplication is from the codomain. Therefore, the linear map is said to be operation preserving. In other words, it does not matter whether the linear map is applied before or after the operation of addition and scalar multiplication. By the associativity of addition operation denoted as plus sign and vectors u1 comma dot up to un belongs to V, and scalars c1 comma up to cn belongs to K, the following equality holds. When you operate L on c1 u1 plus dot plus cn un, the result is equal to c1 Lu1 plus dot cn Lun. So this is the extension of, or this is the generalization of these two conditions which we have stated above in the definition. Let us see some examples. Check whether the following are linear transformations. First is, let L from R3 to R2 be defined as L of x comma y comma z is equal to x comma y plus z. So here our function is a function from L from R3 to R be defined as L of x comma y comma z is equal to a vector x comma y plus z. Okay, so we are operating L on a vector of R3 and we get a vector of R2. And second function is L from R3 to R2 be defined as L of x comma y comma z, sorry, L operating on a column vector x y z, and we get a column vector x y from R2. So we have to check whether these two functions are a linear transformations. Let us write the answer for this question. Consider first, in first case, given function is defined as L from R3 to R2 and it is defined as L of x comma y comma z is equal to, we get a vector from R2 and it is nothing, first component is x and second component is nothing but the addition of y and z. Second and third component of vector in R3. So definition is very simple. Now to prove this function is a linear transformation, let x is equal to x1 comma y1 comma z1 and y is equal to, here must be a second vector, must be a y is equal to x2 comma y2 comma z2 be any two vectors in R3. Let x is equal to x1 comma y1 comma z1 and y is equal to x2 comma y2 comma z2 be any two vectors in R3, and let c comma d belongs to R be any two scalars. Now consider L of cx plus dy. So we will show that L of cx plus dy is equal to c into L of x plus d into L of y. So how to show this thing? We go step by step. So c here is equal to L of c into x vector is x1 comma y1 comma z1 plus d into y vector is x2 comma y2 comma z2. So we multiply by these scalars to these vectors in the next step. L of, now the first vector is cx1 comma cy1 comma cz1 plus second vector is dx2 plus dy2 plus dz2. Now inside the bracket this is the addition of two vectors and we know that how to add these two vectors. We add these two vectors component wise. So L of cx1 plus dx2 comma cy1 plus dy2 comma cz1 plus dz2. Now by the definition of the function L, when function L operated on the vector with three components, then we get a result of a vector with two components whose first component is cx1 plus dx2 and second component is nothing but the addition of last two components of the vector with three components, and it is nothing but cy1 plus dy2 plus cz1 plus dz2. Now we can now this above vector, in the second last step the vector is a vector with two components and that vector is nothing but the addition of two vectors. First vector is cx1 comma cy1 plus cz1 and plus second vector is dx2 comma dy2 plus dz2. But by definition of, let us take c common from the first vector and let us take d common from the second vector. C into this vector is nothing but the definition of L of x1 comma y1 comma z1 and plus d into L of x2 comma y2 comma z2. Thus, so finally we must have to write is equal to c into L of x plus d into L of y. Okay, so this shows that function L is linear transformation. This shows that function L is linear transformation. So this shows that function L is a linear transformation. Now consider the second example. In second case, given function is defined as L from R3 to R2 and it is defined as L operating on a column vector xyz and we get a column vector xy. Now to prove this function is a linear transformation, let x is equal to x1 y1 z1 column vector and y equal to x2 y2 z2 be any two vectors in R3. Let c comma d belongs to R be any two scalars. Now let us consider again L of cx plus dy and finally we show that it is equal to c into L of x plus d into L of y. So it is equal to L inside the bracket c into x vector is x1 y1 z1 plus d into y vector is x2 y2 z2. So we multiply by these scalars to these matrices, these column matrix. So L into bracket, first column matrix is cx1 cy1 cz1 plus second column matrix is dx2 dy2 dz2 and we add these column matrices and we get again a column matrix L of cx1 plus dx2 cy1 plus dy2 and cz1 plus dz2 and by the definition of L we get a column matrix with two rows. First row is cx1 plus dx2 and second row is dy1 plus dy2. Sorry, there is one mistake, I think. No, not there is no mistake. So we get a column matrix with two rows cx1 plus dx2 and second row is cy1 plus dy2 and that column matrix is nothing but the addition of two column matrices. First column matrix is cx1 cy1 plus second column matrix is dx2 dy2. Let us take these scalars outside. Okay, and it is nothing but c into L of x plus d into L of y. Okay, so in this way, here also we have shown that the L is a linear transformation. This shows that the function L is a linear transformation. Okay, so now let us take one homework for you. Question number 1. Let L from R3 to R3 be defined as L of L operating on a column matrix X, Y, Z, and we get a column matrix X plus Y, 2Y, Z. Check whether L is a linear transformation. So try to solve this example at your own, and if you have any query you can ask, you can contact, and thank you for paying attention. Thank you very much.